Hello and a warm welcome to my new YouTube channel. We're going to go through the May 25 paper 2 for the standard level in time zone A. First question is draw the Lewis formula for a HCN molecule. I'm sure you've all seen HCN in your lessons, and we know that hydrogen is bonded to the carbon with a single bond and a triple bond to the nitrogen. Next question, state and explain the molecular geometry of HCN. Well, there are two electron domains, so the only structure it can be is linear. Next question says HCN is a polar molecule. It is. Deduce which atom carries a partial positive charge and which carries a partial negative charge. Well, we know that the nitrogen has a lone pair of electrons on the outside of the molecule. We know that carbon will therefore be polarized by an absence of electron density, which the nitrogen has. Remember, it's relative to each other. So the carbon is slightly positive, that's what the delta sign means, and the nitrogen is slightly negative, the delta sign on the nitrogen at the end of the molecule. Next question, explain why nitrogen gas has a lower boiling point than HCN. Whenever we hear the word boiling point or the words boiling point, we immediately think of our intermolecular forces. Nitrogen, as you all know, is N triple bond M with a lone pair of electrons on each of the nitrogen atoms, and HCN we've just been looking at in the previous question. So explain why this is lower. So this is low and this is high. It's good practice to write out the details from the question. Under the question, have a scribble on the exam paper. That's really useful to do. If it's a simple covalent molecule, then we're going to have van der Waals London dispersion forces, the weakest type of intermolecular force. If it's HCN, we have a permanent dipole. So we're going to have dip-dip, or delta plus delta minus on the molecule with neighboring molecules, which is a stronger type of intermolecular force. Therefore, the HCN has a higher boiling point than the N2 because it has stronger intermolecular forces. Moving on, HCN acts as a weak acid in aqueous solution. Well, an acid is a proton donor to solution, according to Bronsted-Lowry. It's a weak acid, so make sure you put in the equilibrium arrow in your response. That's H2O. The proton is going to be donated by the HCN to the water to make hydroxonium ion plus Cn minus H3O plus. This is showing acidic behavior. I should really put in my state symbols, AQ, AQ, to make sure I get the mark. Don't miss those off. It's asking two ways I could determine that a solution is 0.1 mole per decimeter cubed HCN. So I've got HCN, 1m, and I've got 1m HCl. How could I tell those apart? Well, when I'm ever asked about weak and strong acids, I certainly always mention to my kids, the first thing you should be looking at is a pH meter, because a weak acid is referring to the extent of dissociation, very much to the left-hand side in the equilibrium, and a strong acid is fully dissociated. A pH meter and a conductivity meter are basically the same thing. Put those in, and you will get the mark. There we go. pH or conductivity meter. Method 2, well, you could react it with, I don't know, you could react it with magnesium, Mg. You react it with calcium carbonate, and the acid, this will react quicker, and the weak acid will react clearly more slowly. So, why the pen is doing that. So we can compare and contrast those two things.